I don't know. Can you hear me, Lori?
Lori, can you hear me?
I can hear you now. Thank you.
Okay, good.
Yeah,
So I just finished the introduction. I just want to go over the introductions again. So the panelists here are Dr. Lori Glaze, Director of NASA's SMD's Planetary Science Division at NASA headquarters, Dr. Robert Herrick, Professor at Geophysical Institute at the University of Alaska, Fairbanks, and Dr. Scott Hensley, Project Scientist at NASA's Veritas and ESA's Envision mission to Venus. And Dr. Glaze and Dr. Scott Hensley are both joining us virtually. So Lori, I just want to turn the podium over to you.
Great. Thank you so much. I really want to thank everyone for joining us today to talk about some really interesting new Venus science results. Of all the planets in our solar system, Venus is particularly interesting because in terms of size and mass, it's very similar to Earth, and both planets also formed in the same part of the solar system from the same basic building blocks. And yet the conditions on the two planets today couldn't be more different. As we seek to understand that history and the future of our own planet, such as the effects of climate change, studying Venus and unlocking new findings about its evolution can help us understand our own home here on Earth. In addition, the more we learn about the characteristics of the planets in our backyard, including Venus, the more we can apply to understanding distant exoplanet worlds. Some of the most important data we have for Venus are those from the Magellan mission. Between 1990 and 1994, Magellan returned radar images of Venus's surface geology and mapped its gravity field in unprecedented detail. And from these data, we learned that the surface on Venus is very young, less than about 1 billion years old on average. And based on those Magellan data and data from other Venus missions, our science community have established a really compelling set of reasons for us to go back in a coordinated manner. And we're really excited about 3 upcoming missions to Venus. NASA is leading the Da Vinci and Veritas missions. And then European Space Agency is also at a similar time frame leading the Envision mission with some NASA participation in that mission as well. And when these missions fly at the end of this decade and early into next decade, the science community is going to have a powerful synergistic set of new data to understand how Venus formed and how the surface and atmosphere changed over time. In addition, there's strong interest in Venus exploration by other international space agencies, as well as private commercial ventures, resulting in what we're calling the Decade of Venus. So combining insights from all of these missions, we'll have the opportunity for science results that are greater than the sum of their individual contributions. And that is what's going to allow us to resolve some of these really long-standing questions. One of the biggest questions we have is there active volcanism on Venus today? Understanding the answer to that question is going to help us understand how volcanism has shaped Venus's young surface over the last 1 billion years. So with the help of Magellan and this new study you're going to hear about today from my colleagues, Robbie Herrick and Scott Hensley, this study really provides some tantalizing clues that are going to set the stage for that Decade of Venus. So with that, I'm going to hand it over to Robbie Herrick.
All right. Thank you, Lori. And let me see if I can advance the slides. Nope. Hold on. All right. Shift a little bit over here. Okay. Sorry about that. All right. So this is the big discovery slide. And so for those of you that don't look at radar images all day, I'll try and do a little bit of orientation for you. So what you're looking at on the left and the right are 2 images that were taken 8 months apart by the Magellan mission. And to kind of give you a feel, this is radar and not aerial photography, but there's enough of an analog that I think this explanation will work. So in the first image, you can envision that both images have been taken by, you're in an aircraft, a northbound airplane traveling pretty high altitude and you want to look down at a piece of ground that's about 20 miles across. And so the way that Magellan worked, the first image there would be taken as if the patch of ground was out the left side of the plane. So you would be looking out the left window, looking off to your side down at the ground. And the lighting conditions would be as if the sun was off to your left as well. So off kind of to the west. And then the second image, however, would have been taken from a slightly different orientation. And now the same patch of ground is off to your right. So you have to look out the right side of the plane. And now the sun is also off to your right, so off to the east. And so what that means is that there is a lot of stuff in here that looks slightly, or somewhat in some cases not slightly different because of the different illumination conditions, and the topography causes some of the features to be shifted around. But what has definitely changed between those two images and is not attributable to the difference in viewing is the feature there that is labeled with a gigantic arrow pointing to it. And what you're looking at there is a volcanic vent, or maybe you should say caldera. It's a mile and a half across. And in the first image that Magellan took, it's looks like it's got a deep conical depression, maybe a few hundred meters deep. And maybe there's a couple of small pits just northeast of that bigger circular vent. But then by the time you get 8 months later, you can clearly see that that feature has become considerably larger. The vent is now sort of kidney shaped, and now it actually looks much shallower and has kind of a radar dark interior. And that is a volcano that has erupted on the surface of Venus. And what is probably filling that vent is a lava lake that that probably formed in the 8-month interval, and I would guess was probably still active when the second image is taken. And just for comparison, there's another feature in there that did not change, but a vent that did not change, but looks similar. Looks a little bit different between the two images because of the lighting conditions, to give you a comparison. And then downhill from the vent is to the north. You can see an area there that looks like it became quite brighter in the second image, and we are interpreting that as a likely set of new volcanic flows. That's logically where, if flows occurred, where they would go. However, we do want to be sure we put the right qualifiers on there. We cannot entirely rule out that change, that difference in brightness as being attributable simply to the different viewing conditions. So that's the discovery. Why does this matter? So Lori alluded to that a little bit, but so there was plenty of evidence that Venus is a geologically young surface, and that there was going to be that volcanism is occurring on the surface of Venus, and that there would be volcanic flows in the future. But what volcanically active means, in especially the way planetary scientists talk, it could be months or years or 5,000 years before the next volcanic eruption. And so just as a counterexample, there are places on Mars where there are geologically young lava flows. However, there hasn't been a hint of volcanic activity in the 50 years that we've been looking at the search at the surface of Mars, and probably if you were to poll planetary scientists on when the next eruption would be on Mars, the guesses would probably come in around tens of thousands of years from now, or even longer. So that's why this is really significant. We now know that, of course, extrapolating from a data set of one is dangerous, but it could be that we saw the one thing that's happened on Venus in the last million years. But I think most people would say that this is pretty good evidence that as a planet, Venus, in order for us to catch an eruption occurring just over an 8-month interval means that probably eruptions occur on Venus relatively regularly, maybe on a few months time frame. Kind of the analog is that, for instance, Kilauea, the Hawaiian, the Big Island of Hawaii erupts every few years. On Venus, there's a few dozen volcanoes that have geophysical signatures and look somewhat similar to the Hawaiian Big Island and overall. And so it's reasonable to, that also leads you to a conclusion that, there's likely going to be eruptions every few months. And so with that, I now want to give you a little bit of the backstory on what we found. And let me see if I can, there we go. All right. So, Magellan imaged that. So Magellan mission collected data for a little over 4 years, but it only imaged the surface for 24 months of that period. It went everywhere. It went over every place on the surface 3 times. So once every 8 months. But during the course of the mission, the spacecraft was deteriorating in some ways that meant that on each data collection, the area of the planet that got imaged kept reducing. And also each time it went over, it was the purpose was not to look for changes with time, but to do different tasks each time it went over. So the viewing geometry changed with each of those times. And so in the background there, you can see that the first time around, it caught a bunch of the planet. The next time around, in red, it caught a substantially less amount of the planet, and it viewed in the opposite direction from the first time around, mainly to capture imaging of the south pole of the planet, which is why most of the red area is down in the southern hemisphere. And then the third time around, the goal was to do some stereoscopic viewing, and so it collected data once again from looking out, going back to the plane analog, looking out the same left side window again. So why didn't this get done? This sort of search for something new get done way back when the Magellan mission was operating? Well, basically, in order to do the sort of search that we did for new activity, you need to be able to load in a few hundred gigabyte data sets and move around and pan around on the surface and zoom in and out. And that sort of hardware and software capability for somebody with a normal desktop computer didn't really come into being until the last decade. The software we use is different, but it's tailored for planetary scientists, but it's sort of in the same neighborhood as Google Maps or Google Earth. So that's kind of, when you can think about when that came on the scene, that's roughly when we were able to sort of start doing this type of search. So to go into a little bit about how I did the search, the area that you see that has the colors is all the area of Venus that has been looked at more than once. And so on this map, so you're talking about that area is about, I don't know, 40 or 50% larger than the total land area of the Earth. And so it's still quite a task to try and get that whole area. And in fact, I didn't do that. I had a list of sort of my 50 top places that I thought there might be new volcanism. And I started with the areas in the green and the yellow where we had imaging from the where we're looking, our images are looking out the same side of the plane because that's a lot easier to work with, and didn't have much success there. And finally bit the bullet and started working with the data taken from opposite sides of the plane. And that's when I hit pay dirt in this area that is outlined in yellow here. And that just happens to be, if I can go forward, that happens to be an area that is, if you were to poll people before we made the discovery, they would have said this is the most likely place on the planet for there to be active volcanism. This area has has the largest, the feature labeled Mont Mons is the largest volcano in terms of height on the planet. There's lots of, it has the geophysical signature of having a massive hot plume under it, much like Hawaii and Iceland do today. And there was some other data that suggested there were unweathered or very young lava flows near the summit of this feature. And so if you're looking at the image there on the left, the little black box is the black box is, in both of these images, is the discovery area. So going from the image on the left, we're zooming in now to the summit of Mont Mons on the right. And the tippy top summit region with some very large calderas is down at the bottom of the right image. This is the colors you see are topography where whites and reds are high and blues are low. And then the area that I showed in the first slide is this black rectangle, and so the vent that changed shape is whoops, let me go back if I can do that. All right, let's see if I can, there we go. So the vent that changed shape is on the north side of a larger volcanic complex that is also on the north side of the main summit area of Mont Mons. And so, and Mont Mons is not only is it 9 kilometers high, it covers an area that's over 1,000 kilometers across. So we're looking at a very small part of a gigantic volcano here. So going back to, we're now looking at the discovery area again, and cycle 1 and cycle 2. And another thing that we can do with those two images is where things have not changed, we can pick points that we think are the same place in both images, and we can get a little bit higher detailed topography. And the reason to do that is that we can then use that topography to do a little bit of shifting of the images called orthorectification to make it look like you're looking straight down overhead at the features that have changed. And the reason that we wanted to do that was to aid in the modeling that my co-author, Scott Hensley, who is on the line, did. What we wanted to do was do some forward modeling because these images were taken with such different viewing geometries. We really wanted to nail down that the difference we saw in the vent could not possibly in any way be a factor of simply looking at the same feature from different angles. And so with that, I'm going to go to the next slide and turn it over to my co-author, Scott Hensley.
Thank you, Robbie. So I'm going to go into a little detail about the work we did to convince ourselves that indeed we found something new. So Robbie approached me after he found his discovery and said, Scott, what do you think? Is this really a real change? And I was immediately cautiously optimistic and excited because it did look real. But there were a couple of times, even during the Magellan mission, where people were looking for these changes and they were all traced to being radar artifacts. We wanted to be very careful here that we really had something. So a lot of these features, if you look at them, as Robbie had said, looking either from the left or the right side of the aircraft, most of these things that look very different from each other are actually due to the illumination differences and the topography, the shape of the topography. So the green arrows report to things where if you were to, you have to sort of use your imagination or your radar imagination. And what Robbie was able to do is filter these things and say, for all these ones with the green arrows, this really could be explained just by a change in the looking direction of the two. Now, the big yellow area that's outlined here, that's an area that Robbie had mentioned might be a new flow. But because not only are we looking at these from different directions, how steeply we're looking at them also change between the two. Where in the image on the left, we're actually looking more steeply than on the image on the right. And because that area is a west-facing slope, it turns out because of the way radar works, it can also bloom up and look brighter that way. So that's why we're not saying for sure that there's a new flow there. This might be just due to the way radar works and the way the radar forms images. So again, we want to be cautious about that particular feature because it's hard to be sure one way or the other. But it fits with the story of the volcanism that we were talking about before. And finally, we have the actual vent that we think where we really believe there is change. And this is the one where Robbie was able to filter out visually and say, yeah, I cannot explain this the way I can explain all the other features. And that's why we looked at that. So the question is, well, what do you do then to convince yourself that you do really have a change on the surface? So if we go to the next slide, what we do is we do a mathematical modeling. We have the ability to actually synthetically make radar images if we have enough information. And the information we need is a shape of the vent. So what you see on the left is a profile through the vent. So we need to know how deep it is. As Robbie mentioned, we thought the vent was about a couple hundred meters deep before it had changed. We need to know how wide it is at the top and the bottom. And we noticed it's about a mile wide at the top and a little bit narrow at the bottom. And that determines how steep the sides of the vent are. So what we did is we took and we mathematically modeled a whole series of vents with different depths and different steepness of the walls. Now, how bright a radar image looks depends upon the angle between the line of sight and the perpendicular to the surface. And the perpendicular to the surface is denoted in red here. And the bigger the angle, the darker the surface tends to be. So we can figure out how bright or dark the surface is depending upon that angle, which we can compute. And the other important thing that we need to know is if a portion of the terrain was shadowed or not, because we don't get any return back from those areas. And they look very dark in the image. So over on the right-hand side, we have a whole series of simulations that we've done, not all of the ones we did. Here, we showed about 60 simulations in the paper that we wrote, and we did hundreds of them by ourselves while we were looking for the various examples. And what we can see different brightnesses between the two different cycles. We look for the shadowing, the very dark areas in the interior of the vent. So we like to see how big that is. We like to see how bright the rings are and where they're shaped around the two different images. And I have two examples here where we changed how steep the slope was facing toward the radar. Can you go back, Robbie?
Let me see. All right, hold on. Sorry about that.
Yeah. So the top image is basically a flat surface, and the bottom one is facing fairly steeply toward the radar in the first image. And you can see how different these images look between the two. And so what we were doing is we were going through and visually looking through all these various simulations to find the ones that most closely match the real data. So if you go to the next slide.
Oh, hold on, sorry. There we go.
There we go. So this image you already saw at the top, which was where we have the change vent, and the unchanged vent that we were looking at before is labeled B, and our change vent is labeled V here. And on the bottom, we have zoom ins of those areas along with the corresponding simulations. So the real data was on the left and the simulated data is on the right. And these are the ones that we decided look the most similar from all the simulations that we did to the actual data itself. We also were able to compare how bright they were between the two different images. So we actually quantitatively looked at the brightness levels in the yellow rectangles and the blue rectangles in the simulations to compare them. And what we found is we got a fairly good representation for the unchanged vent in both the cycle 1 and cycle 2 images. We were able to get a good representation of the unchanged vent in the cycle 1 image. But in the change vent in the cycle 2 images, which is shown over there, as Robbie pointed out, none of our simulations could mimic the kidney shape of the vent, nor could did any of our simulations show a very dark floor throughout the entire area of the vent. So based on that, we concluded there was really no way that the radar imaging geometry itself could account for the change in the imagery that we saw. And that's what led us to very strongly believe we had a real change on the surface of Venus. And so with that, Shreya, I'll turn it back to you.
Right,
sorry.
Thank you.
Sorry, one last slide, very important slide. So one we might ask, and this is something Lori brought up at the very beginning, will we ever be able to go back and look at this in more detail and really confirm this again, that what we saw is real? Well, what we just saw was the Magellan imagery, which has been a mainstay for Venus scientists for the past 30 years. Luckily, as Lori pointed out, we're going to get a whole new set of data from upcoming missions. I'm going to talk about the Veritas and Envision missions because they have radars. And radars are important because we need them to be able to see through the surface, through the thick clouds of Venus. Now, these new radars have properties that are going to make them even better than Magellan for looking for activity on the surface. One of the things that's improved about them is they have better resolution imagery, sometimes up to 10 times better resolution. We're going to get 30-meter imagery globally with one of the missions, and both missions are going to have 10 to 15-meter imaging modes for really fine resolution looks at the surface. The other thing about them, as Robbie pointed out, we had this left-right looking out of the aircraft window, so to speak, change in the Magellan imagery. With Veritas Vision, most of the data is going to be acquired looking out one side of the window only. So we won't have this change in look geometry that complicates our ability to look for change. So that's going to make our job easier for doing that. And on Veritas, we're actually going to operate the radar in a particular mode called radar interferometry, which is the most sensitive way to look for change. In fact, we can see 1 centimeter changes vertically in the surface between imagery with Veritas. And by combining data from all the 3 missions combined, basically we can look at change at timescales from 6 months to 4 decades. So it's going to be a really exciting data set, and the whole Venus community just can't wait to get their hands on these data. Thank you. Now, sorry, turn it over to you now.
All right. So did you want to, should we try and get people's faces back on the screen? I'm not sure how to do that or not, either way.
Well, thank you so much. What we'll do is we'll now start taking the questions. And anybody in the room, any questions around in the room? No questions? Oh, okay, go ahead. Please identify yourself and also give your affiliation.
Hello. Hi, my name is Colby Osberg. I'm a PhD student at UC Riverside, and obviously excellent work. Any Venus publicity is great publicity, and this is awesome stuff. So congrats again. So I was just curious. So with Magellan, we are limited to looking for change just in the areas at which we have both a left look and a right look. But with these other missions, we can kind of compare the global images from Magellan to the newer radar that we'll get from these new missions. So we could possibly see even more change in other areas that we couldn't see with Magellan, which is great. And I was just curious as to whether the difference in resolution, so we'll get finer detail in these newer images, whether it will be difficult to tell that things are actually changing, or if they are physically still the same, but they look different in the newer images.
So can everybody hear me? Okay. And Scott may want to comment on this as well, but basically the mission teams for both missions have a whole set of criteria for which they'll be using to sort of, as you sift through, deal with the fact that the newer missions will be operating at slightly different at different wavelengths than the Magellan mission did, and as you pointed out, they'll have higher resolution. They'll also have higher signal to noise ratio, and so contending with that, so to give you a short answer, it will be the limiting factor will be Magellan, and looking between Magellan and the future missions, and that it will be more challenging to look for changes between Magellan and the upcoming mission than it will to be looking for changes during the other missions. And I think that'll probably translate into the fact that, it'll simply take a bigger change between Magellan and the upcoming missions to be, for us to be sure that we've seen a change, whereas we'll be able to see much smaller scale changes during the two new missions. So did you want to add anything, Scott?
Yeah, I'll add just two quick remarks to what you said, Robbie. One of the other data sets that's going to come with Veritas is global topography with 80 times better resolution than is available with Magellan. So whereas I had mentioned that we had to assume a profile for the vents for our modeling, we will actually have topographic measurements that we could actually use to simulate data directly with actual measurements instead of having to have assumed profiles. And that will expand and help us across all three mission data sets. And as Robbie pointed out, Magellan is going to be the limiting thing at that 40-year time scale. But we'll also be able to change between Veritas and Envision. And there we can actually look for changes in this finer resolution data, which is looking at things at finer scales, where change is more likely to occur. So we actually expect and hope to see more activity when we can compare things between Veritas and Envision than just between Veritas and Envision and Magellan.
And I'll add one additional comment just to beat this into the ground. So another thing that we will be able to do with the Veritas data is with the Veritas topography data, is we will be able to take all 3 cycles of Magellan data and do that process of that process of orthorectification that will enable us to, which basically makes it look as if you're looking straight down. And so and so we will confidently have places exactly co-registered between all the both the Magellan data and the new upcoming data, and that will make the job of looking for changes much easier as well. So right now, when you try and go back and forth, there's some shifts in the data that have to do with that issue of not being orthorectified.
Okay, thank you very much. Okay, now Any other questions in the room? Okay, if not, then we will go online. And Julie, would you take it, please?
Sure. So we invite virtual participants to use the raise hand feature in Zoom to ask a question. You will be prompted to unmute yourself. Please state your name and affiliation first, followed by your question. Is Dan Bross online? We're ready for you to unmute yourself.
Yes, good morning. I joined a little bit late, so I was hoping you could restate for me the difference between viewing the initial images, 30 years ago, and what enabled you to make these conclusions more recently. Was it a technology change or just looking at the data in a different way?
So yep, you did miss that part, but that's okay. Good morning. I know you're in Alaska, so anyway, yeah. So to elaborate a little bit more, so when Magellan was active, it was the very first planetary mission where the data was distributed digitally, and it was distributed digitally on a relatively new storage device known as a compact disc. And the first round of data distribution, and it was so much data that only a few percent of it was distributed at full resolution. And it took about 15 seconds to load a single 1024 by 768 tile of data. And so the type of analysis that resulted in this discovery really required the ability to pan around a few hundred gigabyte data sets and zoom in and out. And so you can sort of think about when Google Earth or Google Maps came online. That's about roughly when the technology, both in hardware and software, had advanced enough to do this type of search.
Let me add one other thing, Robbie, to that. And this is something that may be obvious or not. And that is, this is still a manual task when you're looking at data from opposite side looking on the radar. There's no automatic algorithm that will allow you to search for those change. So you do need that new technology for displaying things, because we can't write mathematical code that can automatically search through all the data to find that. Some types of things we can, but on this, what's particularly on opposite side looking radar data, it's still a person in the loop that has to be able to do that kind of detection.
Okay, thank you.
Okay, we're ready for our next question.
Hi, this is Monica Young from Sky and Telescope. Can you hear me?
Yes.
Okay, great. Thank you for doing this press conference. I was wondering, this is just a really basic question. I was wondering if you could just define the term that you used in the paper, the drained post-eruptive event, especially drained and post-eruptive. I wasn't quite sure what you meant by that.
Okay, well, so, there's not a whole lot of pixels to work with, and I should state I'm not a true volcanologist, so I hope my volcanology terms are okay. But basically, after an eruption at a basaltic volcano, you fill up a magma chamber and you get enough pressure, and eventually you have an eruption and things comes out on the surface, and eventually then the source of the hot material is, you run out of stuff, and then usually where things are coming out kind of drains away, and you end up often with something that's got something that is circular with a bit of a raised rim and kind of a conical interior. And so that's and that's after the eruption is finished. And then you might, if the magma chamber is still down there and still getting fed every now and again, you might get a later eruption in the exact same place, and it might be bigger and it might subsume that vent, and you end up with a larger caldera, and the active magma is forming a lava lake in the interior, and there's pulses of magma coming up and spewing over or finding places to come out. I see a more experienced volcanology person in the room, and maybe Paul will correct me if I got any of that wrong. But okay, he's given me a thumbs up and says I did okay. So,
all right, thank you.
Thank you. Okay, next question, please.
Okay, we're ready for our next question.
Hi, this is Miriam Kramer with Axios. I have a question for Lori. So I wanted to ask about the Veritas mission, particularly because it's so relevant to this talk. Arguably, like the findings released today is the best argument yet to launch Veritas, but the NASA budget request effectively zeroes out the mission except for minimal science team funding. I'm wondering if you can talk at all about how that budget decision was made, sort of what that means for the mission going forward. Thanks.
Sure. Yeah, and I really want to make sure we keep a lot of this discussion focused on these findings, which is fantastic. But you're right that the Veritas mission will make major contributions in exactly this area. So we're really, really looking forward to flying Veritas in the future. We announced in the fall that after following the independent review board assessment of Psyche and its delay, one of the recommendations was to potentially either cancel or delay work that's already at JPL or potentially not assign new work there. And so the short answer to all of this is that in response to that IRB report, a decision was made to postpone the Veritas launch to no earlier than 2031. It's about a 3-year delay. Certainly the intention is still to fly Veritas. You can see the time frame listed here. It is true that the current budget that just came out doesn't show the funding profile. That's because we're waiting to work with the project to get an appropriate budget profile to lay in, so that we're not guessing at what that budget profile will look like in the future.
Another question.
Okay, we're moving on to our next question.
Hello there. It's Ivan Semenek from the Globe and Mail in Toronto, Canada's national newspaper. I was hoping to persuade you to use science to get a bit poetic here, Venus, and to kind of describe what this eruption might have looked like if someone could actually safely observe it up close. Venus, obviously, as was mentioned at the beginning, is similar to Earth in many ways, but obviously the atmosphere is very different, much higher pressures, much higher temperatures. How would that affect the eruption, given the kind of material that's coming out? Would it run farther, longer, hotter, or what would it look like?
Okay, let me see how poetic. Well, of course, yes, we have not a lot of pixels to work with, so I can make up all sorts of stuff. But I will say a lot of this is speculation in part, and that's why we want the future missions, is so we can see an eruption developing and get the time scales and paces of individual flows, and in some ways Magellan is low enough resolution that in a lot of cases we're not sure whether we're looking at individual flows or lots of flows, and we definitely don't have enough information to say evaluate with much confidence, how the flow developed and, shifted between Pahoehoe and while it was going. Anyway, all sorts of things. But if I were to make a in most ways, the flows are going to be everything on almost everything on Venus, especially the giant volcanoes, are reasonably analogous to something like Hawaii or Iceland or the Galapagos Island, or I think it was Las Palmas that erupted, was it last year? And so basically big basaltic shield volcanoes, so pretty analogous to those, very different from what we call the arc volcanoes. So something like Mount Fuji or the Cascades that are all often erupt quite explosively. So pretty similar. The higher surface temperature on Venus, for the air, means that the lava flows are probably even runnier and long-lived. And so even compared to kind of the broad basaltic shield volcanoes on Earth, the Venus volcanoes are even flatter and wider. And so, a lot of the volcanoes on Venus are, there are many examples of things that are only a couple of miles high, but expand and cover areas that are 1,000 miles or more across. And so so things go quite a bit further. The higher atmospheric pressure is going to make things, and unfortunately on Earth, there's not nearly as much known about subaqueous volcanoes and how those behave, but the pressure that at the surface of Venus is roughly equivalent to the pressure about 1 kilometer deep in Earth's ocean. Of course, the covering material on Earth is water, and it's not on Venus. It's still carbon dioxide. But one thing that does is it inhibits, in even basaltic volcanoes on Earth sometimes have a little bit, or spattering and explosive activity, and even that should be more inhibited on Venus than it is on Earth. And I droned on a little bit. What did I miss that might interest you out of that? It wasn't very poetic, though, was it?
Well, you did say runnier, so that's good. and I appreciate you considering the conditions. And I think it's an interesting comparison with subaqueous on Earth, but obviously a lot hotter. So that's a big difference.
So, and Scott has been silent for a while. He's looked at a lot more terrestrial volcanoes than I have. So if you want to add anything, or maybe Scott can be more poetic than me.
Well, I don't think I can be more poetic, and I'm not a card-carrying volcanologist either. I'm a mathematician, even further divorced from volcanology than Robbie is. But I think what Robbie said, generally speaking, that the thick atmosphere and the higher temperatures lead to the less explosive and a more runnier type flows on the surface. I think that's as far as I'm willing to go with my expertise base.
We have time only for one question because we have to finish at 2 o'clock. So one more question.
Hello, this is Katrina Jackson with NHK. You were talking about the reason why this discovery didn't happen until recently due to the increase in technology of hardware and software. So I was wondering, has the Magellan data set now been fully looked through to the point where you are confident that this is probably the only volcano that erupted during the Magellan mission? And this next part is probably for Lori. Are there any other old planetary data sets that haven't really been combed through yet, where there's the potential to still make significant discoveries like this?
I did, where we made the discovery, like I said, is the most likely place that there should have been new volcanism. But there are other there was a larger list of contenders, and like any actual paid scientist nowadays, once I made the final discovery, I stopped looking and went on to do stuff that I get paid to do. I got a variety of other things. So the reality is that I've looked at roughly 1.5% of the planet, and about a little over 40% of the planet has actually been imaged twice. And there's still quite a bit of, there's still several Hawaii-like volcanoes on Venus that I did not get a chance to search. So there's plenty more to do there. And there's also a variety of ways that people think the planet Venus works. And so it's not entirely a sure thing. It's by no means a sure thing that only these big Hawaiian-like volcanoes are the only places on Venus that are active and that you might find active volcanoes. Of course, I mean, for instance, there's a volcanic field in Arizona that has a bunch that is active and has very small active volcanoes, but some of the larger flows with that would be visible. But the eruptions in that field are once every, I don't know, several hundred years, I think, if I recall correctly. And so by no means has all the potential searching for new stuff with the Magellan data been done. And I know, Lori, I know there's a gazillion old data sets that could be looked at for planetary data, but I'll let Lori comment further on that.
Sure.
And Lori, a question for Lori?
Yeah, she was the second. The question was, are there some other old data sets, planetary data sets that ought to be combed through or could be combed through?
Yeah, and I'll just be relatively quick. I think Robbie stated that there's still, of course, tons of data that still could be combed through and looked for additional information about what's going on Venus, and that includes not just Magellan, but older data as well, Pioneer Venus data, some of the older Venera data. There's tons, but honestly, if you're talking about surface. Trying to understand the surface geology and geophysics of Venus, right now, Magellan is the state of the art. That is the highest resolution we have. We really need to get Veritas and Envision at Venus in the next decade.
And I think the question was, there are other planets that come to mind in terms of old data sets looking for, I don't know, maybe really cool things that come to your mind, Lori.
Sure. Well, looking for active features, certainly, Mars still, we're doing a lot. You can see a lot of active things on Mars, not necessarily volcanism. Robbie mentioned earlier about the long repose periods on Mars for volcanism, but watching aeolian processes and other things on Mars, we do see a lot of activity there. So, and let's talk about Io, right? The most volcanically active body in the solar system. And so we've certainly seen lots of activity there with multiple different spacecraft missions.
Thank you so much, Lori. Appreciate it. And with that, I'd like to conclude the press conference. We really appreciate your presence. So thank you, Dr. Lori Glaze, Dr. Robert Herrick, and Dr. Scott Hensley for joining us today. Thank you.